I want to welcome today another special guest, Rick Wagner from San Diego Supercomputer. Rick is the Chief Technology Officer there, and I want to go ahead and give you the floor here, Rick, for a little intro about yourself and anything you want to talk about in your role that I kind of just mentioned there.
Being the CTO at SDSC, which is part of UCSD, yes, this is my office, and I am up on the campus here in La Jolla, is a very interesting one because SDSC has been a leader for almost 40 years now in, supercomputing, high performance computing, and data initiatives. And now with the growth of AI, and that we've dealt with in the last 20 years, the adoption of the web, it's been interesting to take a leadership role where there's already so many people excelling at bringing technology to researchers, which is really what the focus of SDSC is.
How did you even get into technology in the first place?
Back in 1984, when I was in sixth grade, the Apple computer systems were becoming very widely deployed into the California educational environment. And so in sixth grade, we had an Apple II in our classroom. And there's a classic computer program called Logo that is the turtle, and you go forward and right and left and stuff like that. And students were basically learning it and learning how to draw. And without any formal training, I looked at it and I was like, what is a for loop? And I was able to implement some very simple drawing patterns like drawing and erasing a box. Like we would think of it this day as some trivial animation or something, but if for all of my life I've had that type of thought process, and it's stuck with me. It took me a long time to recognize my own interests in terms of technology. And really it wasn't until I got to my undergraduate degree where I was studying physics, where I learned how much computing could play a role in enabling research, that basically solidified it.
I see that you were in the military for some time, and how did that shape your career in technology, if at all?
This is going to be an interesting acknowledgement of self-denial again, because I joined the Army for a few reasons, one of which was the classic, I needed to be somewhere else. I did not see myself at that time being successful in college, but I wanted the college fund. I wanted to go to jump school, which I did. And I basically took the first job they offered me that got me the college funded jump school, which was chemical operations specialist, which at the level I was in as enlisted primarily means literally vehicle washer, or maintaining protective equipment and stuff like that. And if you just think about all the images from Desert Storm and Desert Shield, of people in chemical protective clothing, that's right when I joined, which is why that job was being filled up. And so I joined to do that. I went through my training. There were some interesting things there on the physics side around, because it's actually the nuclear, biological, and chemical side. And on the nuclear side, it was interesting because we did cover a lot of things about measuring radioactivity, downstream of downwind effects, the ability to protect against radiation through different materials. But when I got to my unit in Germany, there's not a strong need within those units. It was an aviation unit for me to do my day job or my regular job. So I ended up being the company clerk. I could type. They gave me an old IBM PC clone, a Zenith, and I learned about whatever graphics program, basically PowerPoint. Like the commander comes up to me and goes, do you know how to run this? And I was like, no, sir, but I can learn. And I learned that. I learned DB3 or DB4 or whatever it was. And that was basically my job. Because I was adept at computing to the point where when we deployed to Somalia, I took the computers with us so that I could keep doing my administrative job and spent hours with one of my colleagues, one of my friends, playing Snake. We would just sit in the tent, bored out of our minds, driving the Snake around for something to do in the sand and dust.
Well, that's interesting. I really expected chemical operations specialist to be a fancier gig than sort of what it ended up being. But it sounds like you learned a lot anyway because of all the other things that you ended up doing, and that technical or technological interest that you had even as a child just kind of kept going in throughout your time in the military. How long were you in the military?
So I actually did 8 years. I did 4 years on active duty. Again, I was really fortunate. I really enjoyed being in Germany and in that aviation unit. And then I did 4 years in the National Guard, where I actually joined a tank unit and reclassified to being a tanker. And I got to say, if you're going to do something one weekend a month, driving an M1 tank is relatively exciting. And that I wasn't active enough in the company, like the management, to worry about computing. I really just got to show up and be amazed at the technology and engineering in the M1 and how impressive it is.
Oh, wow. So where would you drive that around?
Vermont.
Oh, interesting. Yeah, pick up
Very,
some
very
coffee.
small. Yeah.
Okay, military, great. It sounds like that helps you kind of get a jump start. And then you went into education heavily, mostly physics, but I see a couple other funky little things in there that I'm curious about. I saw philosophy in there. What the heck? I mean, tell me about your journey and how you chose this sort of path.
With the GI Bill that I was on, you had 10 years to spend the money. And it's amazing. So when I got out of one of the reasons I went to Vermont is one, I visited there and I really liked it. And I went to not a great college. As I tell people, sometimes quitting is the answer. And then I moved back to San Diego and I looked and I was like, I have 3 years to basically spend 4 years of educational funding. Do I want this to go to waste? And I immediately started going to community college at night. I cranked through finishing my undergraduate degree, my bachelor's, going from Mesa College, where I got my associate's degree, into UCSD, where technically I finished physics in less than 2 years. I thought I was going to be an engineering student, but I find physics very interesting and I went into that. And then you do the classic thing where it's like, okay, now what do I do? And suddenly grad school appears. And one of the great things is generally you get a stipend. So you get some funding for your cost of living, et cetera. And they pay for your tuition. So my graduate school was covered because the research you're engaged in, that cost is written into the cost of grants. So you lose some of the control of what you get to do. So like I did astrophysics because I liked the professor. I wanted to do computing, and that's the data analysis. Like my PhD, my doctorate basically was a data science research project focused on turbulence within astrophysics. So
Wow.
you do there's some trade-offs. Like I enjoyed it. I probably wouldn't have picked something very different, but I was also boxed in because you take the money, you do the work. So I went into grad school, and one of the odd things is I did my master's degree, which you get after passing what's known as the qualifying exams. And then after several more years, I got what's known as a candidate of philosophy degree, which is called a CPhil. It's an uncommon one that's only granted largely within the University of California. Because once you advance to candidacy, you're basically free to do your research. You don't have to take any more classes. You're still registered as a student, but you're basically supposed to be finishing your dissertation and graduating. But the thing is, at that point, you don't have to take any more classes, and you're not required to stay around. You might notice that there's a large gap between my CPhil in 2009 and my PhD in 2023 last year. That's 14 years. And that was because even though I had completed all the research I needed to, I did something that a lot of people do. I stepped off the track. I started working. I went to work for the San Diego Supercomputer Center as an engineer. I
Mhm.
became a manager. I went to work for the University of Chicago for a data management group. And then I came back to UCSD. Fortunately, my boss at the time in my previous group here at UCSD was, you know what? Go for it. Get your job done. Take the time, write this up. And so after talking with some friends, talking with my old advisor, talking with the department, explaining like, if you'll let me do it, I'll complete it. I was able to defend and finally finish my doctorate. And kind of get that out of the back of my mind. So I have a doctor of philosophy in physics because I found the data and computational challenges and the mathematical aspects of turbulence and astrophysics to be fascinating.
Do you apply any of that into your technology career at San Diego Supercompute? I mean, other than maybe a couple theoreticals here and there, I mean, is there any actual physics that you get to utilize in your day to day?
Other than the fact that electrical power gets turned into heat, which is a critical part of the data center, or the fact that we have to, uh, the team that leads the data center has to hire engineering companies to do computational fluid dynamic simulations for the data center to understand the impact of changing the cooling patterns or where different systems get deployed. In some cases, some of the direct physics does come into play. And then it's more, the systems focus. If I'm up doing this compute over here and I'm storing this data over here, what's the connection between them? What's the bandwidth? What's the performance? What's the fragility? How robust is it? A lot of that comes from a physics and modeling perspective. Being able to think about, if I have all this data or these sensors coming in and I want an outcome over here, what are all the steps in between and what kind of performance should I expect? So some of the stuff I learned like graph theory is phenomenal, super essential. And then in terms of human aspects, something that I use as an analogy is emergent behavior. So have you ever seen like fractals? You look at the Mandelbrot sets and stuff like that. The fascinating things about those is it's very few equations that you're basically iterating, but they come out with these beautiful pictures. And a lot of organizational and business leaders will also point out that if you want people to succeed, or even for yourself, like there's that book, The Power of Habit,
Hmm.
it's not necessarily controlling everything. It's more about the small activities and behaviors. It's more about the questions you ask and the how you get people thinking or doing something that can lead to amazing results.
Oh, wow.
And
Yeah, just
so,
simple equations. If you can nail them down in each of those team members or, colleagues, whatever, that's when you get your amazing fractal.
yeah, it's the exercise every day, even if it's something small. Stuff like that. It changes dramatically, can have dramatic impacts over time,
Hmm.
as opposed to being, the very excessive, like, no, this is the exact steps that we're going to take to do this. And these things apply in different ways. Like obviously, if you're building a large building, there's going to be a lot of clearly defined steps and stages.
Hmm.
But like I've dealt in safety and security, and with safety, it tends to be more about small behaviors and patterns, right? Use what's called lockout tagout on the electrical systems. You put a lock on a breaker before somebody else can't go to work on it, and things like that. So even in the context of major things, like capital investments or projects, small behaviors lead to success, even if the outcome is clearly defined.
Give me a little bit more info on really what you provide for the community or for the university.
So you've actually touched on one of the key ways to think about the supercomputer center is there is a data center, right? And a data center is a very valuable asset to the university because we can host large scale systems. We host several national systems, primarily funded by the National Science Foundation, which are accessible to researchers around the US and some of them internationally. So that's one example of something we do where we host and operate systems for researchers with a broad spectrum of science needs. So they're doing high performance computing or high throughput computing, like small scale batch. And we have a lot of expertise to help new users come on board. And then we've got a lot of capability if they need to run large scale, high performance, tightly coupled applications,
Mhm.
right? What makes a supercomputer is really the network, and how you can, have a coherent performance from a set of computers as opposed to really strong performance on an individual one. So that's one of our examples of a national focus. At the university level, we have some things like we have co-location space. So departments and research groups that need to host dense systems that aren't appropriate for their own facilities, they come in here, and we have ridiculous network connections, hundreds and hundreds of gigabits coming in both for within connectivity within California, nationally, internationally, and on campus. Like the networking here is amazing. We have switches that move terabits. They still like just blow me away. And so for campus, some of the things we provide besides co-location is services like large scale storage that they can use to access data when their systems are in the data center or across campus. And this is just, that's all kind of at the technology level. Then you have the fact that too, you basically end up aggregating expertise around stuff like this. And so you end up with research groups that are able to either leverage this, like CADA, that do global internet data analytics. They leverage some of our resources for studying, basically how the internet works at a global scale. You have Wi-Fi, the project that's run out of Sycor by Ilka Tintas, that does fire modeling for wildfires. And so you have the data center, you have the team that understands that technology, you have the high performance computing team, and then you have these other research groups that either specialize in leveraging some of the infrastructure for research purposes or enabling access to it for others. But you're right, it starts as the fact that you could do this without a data center, but it makes a huge difference to be able to touch the hardware in some cases. And so if you go to our website, you see all kinds of stories, and we have our annual report, and that really tells kind of a full picture of the kinds of things we do.
Everybody's saying that, high performance compute is even more important today, it seems like, than it has been in the past, or at least that's the vibe I get from it all. And a lot of this has to do with AI, because AI is, well, it uses a lot of compute, or it can. Do you see or feel this change in the high performance compute space? And where do you see it heading?
One of the biggest changes that supercomputing and high performance computing have had to deal with is being driven by the commodity market, right? So if you go back to when SDSC was founded, when the first Crays and thinking machines and connection machines and others were coming out, they were driving the processor, networking interconnect, and other technologies. And then with the rise of the web and the hyperscalers, the Facebooks, even the Apples, the Microsoft and Azures and Googles and stuff, the product manufacturing for the technology shifted their focus to supporting them. And so you saw a rise of what we would call Beowulf clusters. Can you take commodity servers and assemble them into what is effectively a supercomputer using off-the-shelf components? And so now we're in this area where sometimes there's still places, not necessarily us, but like especially the Department of Energy, where they'll do co-design and help drive product development in particular areas for their needs. For us, what we tend to be about is, okay, given this space, how do we take the emerging technologies and get that into the hand of researchers to find out what it can enable in terms of new research? Now, the one thing I'd like to point out about AI is NVIDIA and the whole accelerator thing has been fascinating, because NVIDIA recognized within the high performance computing and supercomputing space, a lot of the, like talking about computational fluid dynamics, right? It's a lot, for those of you who still remember or willing to talk about linear algebra, a lot of it is linear algebra. And that does really, really well on a GPU. They can do the array operations and stuff like that. So NVIDIA started hiring academics who are familiar with the applications to port their code to the GPUs to demonstrate the capabilities of the GPUs for accelerating those types of applications. They did a great job of it. And all of a sudden, like, you start to see every computing system had to have at least some, if a full bank of GPUs in it. So it's kind of a natural progression that once machine learning and AI took off and it was all the same linear algebra array operation type math at the hardware level, NVIDIA was right there.
Hmm.
So I got to give them a lot of credit, but it also has the exact same kind of mathematical workload in a lot of ways. And that's where the similarities come in. And we have colleagues, of course, that are supporting that in the commercial space, as same way we are within the academic space.
It's very interesting where NVIDIA plays in this space. And a lot, I mean, most folks in the AI realm or that operate in this, in your world, understand just how important NVIDIA is. And of course, every shareholder has seen how well their NVIDIA stock has done because of much of this. The chips were designed for gaming, and then everybody started mining for Bitcoin with them, and now AI is really what they're being used for. There's also a lot of bespoke processors that are starting to kind of come
Mhm.
out that are designed specifically for AI, even analog AI chips, which are a little
Mhm.
tricky because of noise. Do you see anybody coming or any kind of a market shift that may happen in the next couple years?
I'm interested in this because I think if we compare research to the commercial industry side, in research, we, I think, have less of a need for inference. Basically, you train a model, so you have training and you have inference. You have the trained model, you train it, that takes a lot of data and compute. And the idea is inference is much cheaper and faster computationally. In research, what I have seen and what I expect to continue is that we're primarily focused on training. Because in research, once you can answer a question, you need to go write a new tool, you need to train a new model. And so there'll be a blend. Now, on the commercial side, and this is where I have seen some stuff, is the focus on being exceptionally power efficient at inference, at throughput, for generative AI loads, for others. And I don't know how much of that is going to come back into the research area unless what I expect to see in some cases is where some models become stable. If you think about application libraries, like we have linear algebra libraries, we have math libraries, we have other libraries. I do expect some models to become stable like that, where they don't iterate and rev much. Then we'll have a stronger need for inference. I don't know how much we'll have a strong need for dedicated hardware for. It's really going to depend on the scale of applications. I think within climate science and some other application spaces, that will happen. Where they'll be like, no, this is the weather model for subgrid small scale modeling, and you have to use it or other things. For the broad stuff we see, I think it'll be less of an activity.
I know we're at time, but before we go, I did want to touch on a tiny bit of, personal stuff
Yeah.
about you. I hear you like motorcycles. What are you riding, and when are we hitting the canyons?
Okay. Maybe not too many canyons, but we should go for riding before the weather gets hot. Uh, that is absolutely like I'm looking out and it's been nice and cool in the morning. So I have two motorcycles. I have my 2016 Yamaha XSR 900, which is that three-cylinder engine that was in the FZ09, what is now the MT09, which is just a phenomenally fun bike. It's what we would call a standard bike, which I like that upright riding style. It not quite a dirt bike feeling, but similar to it. You're just sitting up on the bike, but ridiculous amounts of power, kind of like having a car that's got more go than you ever need. And then I have on a much different scale, I have my 2012 Ninja 250R from my uncle. It's got carburetors. I rode it to work today. It's fun for my commute. It's such an easy bike to ride, and that little engine, you're going 45 miles an hour, and you've kept it in like fourth gear, and it's like at 9,000 RPM. It's ridiculously fun.
Well, people don't understand really just how much more fun slow things can sometimes be because
Yeah.
you actually have to try harder. Well, I can't thank you enough for joining today, Rick. This was super fun. The time went by way too fast. And we'll have to chat again at some point. Do you have any closing thoughts or anything you want to plug for yourself or for your organization at all?
I do want to thank you for taking the time. enjoy talking about what's amazing about SDSC and UCSD. And I also, we have a research focus. We are this whole thing about the industry and the development of the technologies, the software and hardware. We live by that, right? For us, our engagement with the people developing or selling these applications and hardware platforms is we rely on them to deliver novel things to the research community to enable new research. Um, at the same time, the researchers rely on us to do the same thing. And so, I'm always interested in talking with folks. If you ever wanted to get a panel of people together, please keep me in mind.
Ooh,
I'd
yeah.
love to do this again.